In the last lecture we saw resolution of identity, and we saw how to develop continuous functional calculus in fact, right. For each continuous function we were able to associate an operator using the resolution of identity we started with, and this was more or less like the Riemann integration or how you prove the Riemann integral of a continuous function exists. Okay, so, now we will see how it figures in spectral theorem. What we are going to do is to state a list of spectral theorems. So, we already saw different versions, one is the projection valued measure, one is as a multiplication operator and so on, right. So, we are going to say that these are all, we are going to prove that these are all equivalent. Okay. So, we will state the resolution of identity form for spectral theorem, multiplication operator form, continuous functional calculus or L infinity functional calculus. Okay. So, these all these statements are equal or equivalent, like if you have one of them you can prove the others. So, that is what we are going to prove. So, that sort of completes this circle of ideas. We have already proved spectral theorem. So, we know that the continuous functional calculus exists for a given normal operator or for a given self adjoint operator. So, we already know such things, and so all the other formulations, whether we use the resolution of identity, projection valued measure, continuous functional calculus, L infinity functional calculus or the spectral measure form, which is essentially realizing the operator as a multiplication operator, all these are equivalent to each other. Okay. So, that is what our aim is now. Okay. So, let us start. So, let me start writing down various various formations of spectral theorem. Okay. So, spectral theorem, this is the resolution of identity form, okay, resolution of identity form. So, we defined resolution of identity in the last two classes and studied its property, and we know that we can develop continuous functional calculus with it, right. Okay. So, let A be a bounded self adjoint operator, bounded self adjoint operator on a Hilbert space H. Okay. So, from now onwards we will assume that H is separable. Okay. So, the it is not necessary for many of these things, but you know sometimes we have seen this before, like if you have a separable Hilbert space, the measures you get can be made sigma finite or even finite, otherwise you have only a semi finite measure, right. So, one can always get somewhat neater statements if the space is separable, and most of the time people work on separable Hilbert spaces. So, on H, which is a separable Hilbert space. Okay. So, we will assume that. So, A is a bounded self adjoint operator on H. Okay. Then there exists a unique resolution of identity, resolution of identity. This is essentially the projection valued measure version. Okay. So, resolution of identity E sub t. So, remember that for each t, E sub t is going to be a projection, it keeps increasing and it increases to the identity operator at infinity and it decreases to 0 at minus infinity, and there is a right continuous assertion along with it, which is right continuity in the strong operator topology, right. That is what a resolution of identity means, and we developed integration with respect to resolution of identity, right. So, there is a unique resolution of identity supported on the spectrum actually, but we will write it as, since we were doing things on an interval minus r to r, we will simply write it as an write that this is supported on interval of that kind. Okay. So, resolution of identity E t supported on Uniqueness is something you already know, I may not stress too much on that. Once you have various tools, you can always prove uniqueness. Okay. So, resolution of identity E sub t supported on minus norm A. So, remember A is self adjoint. So, the spectrum is actually contained in the real line, right. So, it is a compact set in the real line, and we know that the spectrum is contained in a ball of radius norm of the operator, right, here norm A. But I know that it is also contained in the real line. So, it will be contained in the interval minus A to A, right, minus norm A to norm A. It may be much smaller than this. Okay. So, that, but it is surely the resolution of identity, it is surely supported in that interval. So, for t greater than norm A, E sub t is the identity operator. For t less than minus norm A, E sub t is 0. Okay. So, that the operator A can be written as integral t det, right. So, it is essentially on the on minus A to A, you look at the identity function, that is lambda going to lambda or t going to t, and so that is a continuous function there. For that continuous function, we have defined an operator, right. So, the assertion here is that if I take a resolution of identity. So, recall that if I take a continuous function in this interval minus norm A to norm A, where the resolution of identity is supported, we know how to define an operator corresponding to f, right. So, we have defined integral of f det, right, starting from Riemann sums and all that. And so, in our notation, it was phi of f. Okay, maybe I used g. So, just to be consistent with what we were doing. So, this is what we call the phi of g, right. We defined phi n g for each n, and then took as the limit as n goes to infinity, and that gave us this operator, which we denoted by phi of g, but at the end we change the notation to integral of g against this resolution of identity, right. That was a natural notation to bring in, right. It was very similar to what you do in the Riemann integration. So, the function t going to t is a nice continuous function on this interval minus A to A, and so when I integrate t against the resolution of identity, I am going to get an operator. And of course, if the function you are integrating against is real valued, the operator is self adjoint, right. Remember this g going to phi g or the integral g det is a algebra homomorphism, right. So, g bar will go to the corresponding adjoint there, right. But if g bar is g itself, then what we are saying, the operator and its adjoint are same, that means you get self adjoint operators, right. So, the function t, which is a real valued function, will give me an self adjoint operator, and that is your A, right. So, there is a spectral resolution, that means the resolution of identity is a p such that A can be written as TET. So, this is the resolution of identity version. Okay. So, if you manage to develop the projection valued measure from ET, then this is simply that representation we have already seen. Okay. So, one can write it as actually an integral over the spectrum of A. Okay. So, we may not bother about all such finer details. Our aim is to write down various forms of spectral theorem, and most of them will be supported on minus norm A to norm A, and then we will prove the equivalence of all this. Okay. So far we have been able to write down the resolution of identity form. So, let us call this one, let us go to the second one. So, most of this you have seen in some form or the other, right. It is the equivalence which will be new, like if we can go from one form of the spectral theorem to the other form. Okay. So, that is the whole point. So, spectral theorem continuous functional calculus. Continuous calculus form, let us say. Okay. So, again this is something you have already seen. So, let me write this, let A be a self adjoint. So, everything right now is being written for self adjoint. With appropriate care one can write it for normal operators as well. Okay. So, but we will stick to self adjoint operators because the resolution identity etcetera was defined for such operators. A be a self adjoint operator on H, on H. Then there exists a unique star homomorphism. So, that will be an algebra homomorphism. Let us call that phi sub A. So, the A here is the dependence on the operator we are starting with, right. A is a self adjoint operator. So, given a self adjoint operator we have a continuous functional calculus, that means phi sub A, which is a star homomorphism, continuous and all that, right, from continuous functions on minus A minus norm A to norm A, right. So, that is the interval we are looking at. Again, as I said, one can restrict to the spectrum of A, okay, but we will not bother about it, to B of H, bounded operators on the Hilbert space H. Remember, H is assumed to be separable from now onwards, such that it has various properties, such that 1 x equal to 1. So, that is identically equal to 1. So, that is the identity on C minus norm A, right. On the continuous functions on this closed interval, the identity is the constant function 1. Okay. That implies its image, well, it is a homomorphism. So, its image has to be the identity operator, right, on H. And let us take the identity function. So, I d x equal to x. So, identity is the function x going to x, right, on this interval minus A minus norm A to norm A, but that is a continuous function there. So, it has to give me an operator there. So, that will go to, that goes to the operator we started with, right. So, should be equal to A, okay. And of course, the continuity of the homomorphism itself. So, phi A f, the operator norm, is less than or equal to the L infinity norm or the supremum norm of f, right, for every f in continuous functions on minus norm A to norm A. Okay. So, that is the continuous functional calculus form. This is something which you have already seen. So, again notice the difference in the way we are writing. We are not looking at continuous functions on the spectrum of A, right. It is, we are taking this interval because of whatever we did with the resolution of identity and so on. So, we, that is why you do not have the equality at the last line, right. So, you have only an inequality because f, unless you take the spectrum as the set where the continuous functions are defined, you may not get the equality. Okay. So, that is something one should keep in mind. Okay. So, 2, so that is 1, that is continuous. First one was the resolution of identity, second one was the continuous functional calculus, third one spectral theorem. So, once you have the continuous functional calculus, we know how to deduce the L infinity functional calculus, right. So, spectral theorem, the L infinity functional calculus form, functional calculus form. So, what is that? Again, let A be a self adjoint operator on the Hilbert space H, which is assumed to be separable and all that. And so, instead of looking at bounded functions on the spectrum, we will look at bounded functions on minus norm A to norm A. Okay. And let, so remember, for bounded function we use the usual English B, that is minus norm A instead of the script B, right. So, you look at this interval minus A minus norm A to norm A, compact interval, and look at bounded Borel measurable functions on this, right. So, be the space of bounded Borel functions, right, Borel functions on that interval minus a to a minus norm a to norm a. Okay. Then, so the L infinity functional calculus says that for each bounded function you can associate an operator, right, using the self adjoint operator a, which is what we call f of a, right. If f is a bounded function, we can define t sub f or f of a and all that, right, they are all same. Okay. So, then there exists a star homomorphism. Well, this is also unique, but as I said, uniqueness we may not bother too much about it. Homomorphism, let us denote it by phi sub a, because this is going to be consistent with the continuous functional calculus. So, all continuous functions are on minus norm a to norm a, they are bounded. So, they will be in B of minus norm a to norm a, right, and we use the notation phi sub a for the continuous functional calculus, right, the homomorphism that comes from there, and that is what extends to L infinity functions, right. So, phi sub a, we will denote it by phi sub a itself, B of minus norm a to norm a, look at the space, two bounded operators on H. Okay. So, we have a unique star homomorphism such that as above, right, as above meaning the constant function will go to identity operator, the identity function x going to x will go to a, and we have the norm bound, right, norm of phi a f is less than or equal to the L infinity norm of f, okay, as above. So, those three conditions such that, so we have an extra thing here, if f n converges to f pointwise and bounded, then the images are operators which will converge in the strong operator topology, right. So, let me write down that such that if f n converges to f pointwise and bounded, of course, these are happening in the interval minus norm a to norm a, right. So, in minus norm a to norm a, then the image. So, images are phi a of f n, right. So, this would be a bounded operator associated to f n, and this will converge to phi a of f, right, which is the other operator in the strong operator topology, right. So, if you evaluate it at any point x in the Hilbert space H, then you will have convergence, right. So, in the strong operator topology. Okay. So, that is the L infinity functional calculus form. Let us also have the spectral measure form or the multiplication form. So, spectral theorem, the multiplication operator form, multiplication operator form. Okay. So, let us see what that is. So, we can identify our operator A as a multiplication operator on some appropriate L2 space, right. So, let A be a bounded self adjoint operator, then there exist measures. Now, here there is no uniqueness. Okay. So, these measures are not unique. There is a uniqueness statement for the multiplication operator form. Okay. So, I will come to that later if there is time. So, we will do multiplicity theory if there is enough time towards the end. So, right now then there exist measures mu j, okay, j equal to 1 to capital N. The capital N could be finite or infinite. So, N could be finite or infinite, right, depending on what kind of vectors you take and so on. I will tell you that a little bit about it soon, on, of course, all these measures are supported in this interval minus a to a, or more generally depending on how you write these measures on the spectrum, and a unitary map U. So, let us see from H. So, H is the Hilbert space on which A is acting, right. So, A is a bounded operator there. H 2, I have the direct sum of L 2 of R d mu j, right. So, each mu j gives me an L 2 space, right, on the real line. Of course, these are supported in minus a to minus norm a to norm a. So, I can instead of the real line R there, I can put that interval. Okay. So, it does not really matter because the support is this in that interval, and j equal to 1 to n. Of course, the capital N could be infinite also. Okay. So, this is one thing you should notice. I wrote not as an indexing set I and summation over I. Okay. So, in all the previous version you will see direct sum with I in I. There was no mention of what I is. I could be countable, uncountable and so on, right. But once the Hilbert space is separable, you will have only countably many. Okay. So, either finite or countably many, because these pieces we got was were orthogonal to each other, and so you can have only countably many orthogonal subspaces in a separable Hilbert space, right. That is why you have direct sum summation j equal to 1 to n, where n could be finite or infinite. Okay. So, you have a unitary map, and this unitary map, what does it do? It transforms A to multiplication operator on these L2 spaces, right. So, such that U A U inverse. So, U A U inverse is a map from the L2s to itself, right. So, direct sum L2 of R d mu j equal to 1 to n to direct sum j equal to 1 to n, n could be infinite also, remember that, R d mu j, right. So, now it is a map between two L2 spaces, right, concrete L2 spaces, such that U A U inverse is multiplication by x, is multiplication by x. Okay. What does that mean? So, that is, so let me write it in slightly more explicit form. If I take any element in this Hilbert space, it is a, it is coordinate wise, right, it is a direct sum of several elements. So, you take one from L 2 of R d mu 1, the first one, then one from the second Hilbert space and so on, right. So, that is how your arbitrary element will look like. So, that is U inverse A u acting on some arbitrary element there. So, that would be direct sum f j, right, j equal to 1 to n. That is how it would look like. What are fj's? Fj's will belong to the jth element, jth Hilbert space there, right, d mu j, right. So, an arbitrary element in the direct sum will be like this, with the condition that summation norm f j square is finite, right, because if there are infinitely, then you have to put that convergence sequence, a convergent condition, right. So, this is going to be a function, right. So, u inverse a u is a it is not u inverse a u. So, maybe my u inverse went in the opposite direction. So, it should be u inverse here. So, that will pull it back to H, apply A and then go back to your L2 space, right. So, that is u A u inverse. Yeah, here I have written it correctly, u A u inverse, right. So, this is nothing but, of course, this is a function, right, because it is in L2, right. So, I should tell you what this at a point x is, right, and that is simply direct sum j equal to 1 to n, again this could be infinite, x f j x, right. So, I have this f1, f2, f3 etcetera as think of it as an infinite tuple, and each coordinate is multiplied by x, right. If there is only one, it is simply multiplication by x, otherwise there are several copies of that on different measure spaces, right. That is how an arbitrary self adjoint operator would look like on a separable Hilbert space. So, here there is no uniqueness because these measures mu j are not unique, at least the way we construct it. Okay. So, one has to be careful about that, but the uniqueness statement can be made depending on how you choose these measures. So, that is something we will see if there is time, as I said. So, that is called multiplicity theory. Okay. So, yeah, okay. So, 4 versions. Okay. So, our aim is to we will prove that, or to prove that all these versions are same, or prove that all these versions are equivalent. Okay. So, in other words, if I have one of them, I have all the others. Of course, we will prove starting from spectral theorem in the resolution of identity form implies continuous functional calculus, which we have already done essentially, and so on and so forth. Okay. So, all the versions of the spectral theorem are equivalent. Okay. There are many things which I have not written in full detail. One can make many things much more precise, especially the uniqueness part. So, in the first version, the resolution of identity is unique. Okay. These things can be proved independently and it is not very difficult. The resolution of identity is unique. In the second one and the third one. So, second and third, second is the continuous functional calculus form. That means, given a self adjoint operator, there is an algebra homomorphism, and that is unique, and that is easy to see because identity is what goes to A, right. The identity function x going to x has to go to A. So, x square has to go to A square, right. X bar, well, there is no x bar because here there is the self adjoint ones, right. So, any polynomial in x has to go to polynomial in A. So, once the identity goes to identity function goes to an operator A, up to continuous functions in one variable it is already fixed, right, if it is an algebra homomorphism. So, continuous functional calculus is unique. So, if there are two such and identity goes to A, then those two maps will have to be, those two homomorphisms will have to be the same, right, because they will agree on polynomials and polynomials are dense. The same goes for the L infinity functional calculus, because it is extended from the continuous functional calculus, right. So, if you have the continuous functional calculus, you can take limits pointwise and boundedly to get things for all bounded functions. Okay. So, again the uniqueness part of that is also not very difficult. It is the multiplication operator form which you have to be careful about in terms of the uniqueness of those measures, right, because if you remember how we did that in the proof of the spectral theorem, we started with a cyclic vector, right. If I have a cyclic vector, then it becomes easy. Otherwise, then I am taking different vectors, orthogonal vectors, and summing up, right. So, there is no particular order in which you are choosing these vectors. You can choose it in any way you want. Depending on how you choose those vectors, your measures may differ. Okay. So, the uniqueness will come only if you specify a certain way of choosing these measures, or you put conditions on these measures. Okay. So, as I said, if there is time, we will do what is known as multiplicity theory, which will make the this form a bit more precise, in the sense that given a self adjoint operator, we will be able to say there exist measures with certain property, okay, and there will be uniqueness for the measure class. So, remember, the measure is itself is not unique, you can change the measure up to something which is absolutely continuous, mutually absolutely continuous with respect to each other. Okay. So, we will see this at least in the simple case where you have cyclic vectors, where it is much easier to see things, otherwise you are taking a direct sum, right, that is the only difference. So, we will see that we will see the uniqueness for these measures. So, you can call them spectral measures. We will see that uniqueness part when if there is time towards the end, and we will see that these mu j's can be chosen such that mu 1 mu 2 is absolutely continuous with respect to mu 1, mu 3 is absolutely continuous with respect to mu 2 and so on. So, you have a sort of a decreasing sequence of measures, decreasing in the sense of absolute continuity, and then there is uniqueness in the sense that you if you change one of those mu j's, you are only going to get a measure which is mutually absolutely continuous with respect to that particular measure. So, that is a slightly more complicated statement in terms of uniqueness of the measures, unlike the projection valued measure or the continuous functional calculus or resolution of identity and so. Okay. So, well, our aim is to prove these versions are equal, and that is what we will do in the next lecture. So, for the time being we will stop here with all these versions, 4 versions, and we will prove that they are all equivalent in the next lecture. Okay. So, let us stop.